not 30. This is not correct, but at least do you see the page? It's written September 30th, number 2. I should change it to 20th. Yes. Thank you. 20th indeed. So I have 2 more examples. The third type is very similar to the first 2, but still it tells us something. And the fourth one, it has more interesting ingredient in it. So let's see what is our example 3. Example 3. In this case, our age is similar as before, f absolutely continuous, and f prime is in L2. No boundary condition. That's it. Just we assume that f prime is in H2. And what is the inner product? The inner product if of f and g, as in the previous case, we write f prime g prime dt, but that is not enough, because now the constant function are in H, and if we use this, the inner product of 1 and 1 is equal to 0, the normal 1 is equal to 0, which is not good. And to remove this difficulty, I mean, one of the solutions is to add a term here which takes care of the constants. For example, f of 0, g of 0. That's not, I emphasize, that's not the only way to do it. That's one way to do it. And now we obtain a genuine inner product, and the norm squared is f of 0 squared plus integral from 0 to 1 squared dt. It's a genuine norm too. Precisely as before, we can show that it's I mean, complete, everything is going well, and at the end of the day we have an RKHS, so the evaluations are continuous. And even in this case we have the representation. Note that f of 0 is not 0, from 0 to x f of t dt, and using this we can show that ex is bounded, the evaluation. And the question remains, what is e of x? We can provide some estimations as before, but instead of speculating different estimations, we are looking for kx. We find kx, and immediately afterward we obtain the norm of ex. So we proceed to find our kx, and again we need to find a differential equation. Note that our starting point f of x is the inner product of f and kx, which is I mean, by the definition that we have here, is f at the point 0, kx at the point 0, plus integral from 0 to 1, f prime t kx prime t dt. And if we restrict ourselves not to all f, just f being a test function, I mean, of compact support, C infinity, and the support is in the open interval 0, 1. This, as in the previous 2 cases, immediately implies that f of x is minus integral from 0 to 1 f of t kx double prime t dt. Note that when we consider test functions, at the origin and even at the point 1, even in a neighborhood of those points, they are identically 0. So this is perfectly fine. And now we know what is the general solution. The general solution of kx of t was the equation first. As before, the equation is minus kx double prime is delta x, is the same equation as before. And for this, we obtained the general solution, kx of t. I repeat, if I'm not mistaken, it was ct plus d, and here c minus 1t plus d plus x.
Yes, it is correct.
Yes, it was this. Okay, so back to the question which was raised, or comment which was raised before the pose. Now we see that this function kx is not, I mean, kx is not a good notation. Kx is for the reproducing kernel, but at least let me abuse the notation and just say that for any values of c and for any values of d, this function is in this space. Why? Because it's linear, continuous. At the junction, it is continuous. And when I take the derivative, it's just a constant here, another constant there, and it's in L2. And I mean, it satisfies the restriction we want. We want this to be in L2. This is okay. So the function we have is in H, but we want more. What do we want? We want not just for the test function that were used here, not just for these ones. We want for any for any f in H, we want f of x to be the inner product of f and kx. We want this one. And now let's see what is f inner product with kx by the definition. Definition is, here it is. Here is the definition. The value of those functions at the origin. So it's f of 0, kx at the point of 0, plus integral from 0 to 1, f prime, kx prime, dt. And this is t. So it's f of 0, kx 0, as before, integral from 0 to x, and then integral from x to 1. Between 0 and x, we are here. K is ct plus d, so it's just c, f prime t times c t, and for the other one is c minus 1 dt. And even here, instead of k of x at the origin, we can write d, because at the origin for t equal to 0, if you make t equal to 0, we are again here, and kx of 0 is equal to d. Now we simplify a bit. We obtain f of 0 d plus c f of x minus f of 0 plus c minus 1 f of 1 minus f of x. For f of x, we have c times plus 1 minus c. So it's just f of x. That's the good term we are looking for. F of 0, we have d minus c, and f of 1 is just c minus 1. And we want, what do we want? We want this to be equal f of x for all f in H. And this happens if and only if, by considering just even linear function, arbitrary linear function. For example, t and t plus 2, or 2t and 2t plus 1. I mean, just two different linear functions. We see that this happens if and only if d minus c equal to 0 and c minus 1 equal to 0. So in other words, d equal to c equal to 1. And in this case, that's the k we are looking for. K is equal to, when I write the formula, t plus 1 if t is less than x, and if t is bigger than x, is x plus 1. So the diagram is like this: t plus 1, and at the point x it becomes fixed. That's the kernel. And what we need, it is somehow, I mean, not so obvious, the norm of the evaluation is equal to the root of kx of x, which is root of x plus 1. To appreciate this, I go back to the beginning when we had a representation here. This representation. This representation enables us to show that EX is bounded. That is good. But try as an exercise to use this and obtain an upper bound for this. I mean, find upper bound for EX norm. Based on this, we have done this in example 1 and in example 2. You do similar thing. You do Cauchy-Schwarz. I think I forgot prime here, but we can do Cauchy-Schwarz and obtain an upper bound, and then come back here and compare with the optimal one. The optimal one that we obtain. It's kind of, I mean, impossible to use that representation and find this optimal value. Any question up to here? Now to finish this line of examples, as I said, we have different series of examples. One series is this one that we studied, I mean, detail today, is about Sobolev spaces, but we mostly will discuss analytic functional spaces next week. The nature of these two series of examples are different. The last one I consider here is this one, so example 4. H is the set of functions from 0, 1 to R, if absolutely continuous, f prime is in L2. And even I add the condition we had at the very beginning, so it's a bit surprising that, well, it seems we studied this before, but in a vector space, the way we can define an inner product is not unique. The inner product I define in the fourth example is this one. Integral from 0 to 1 f of t g of t plus f prime t g prime t. It's not forbidden. That's another inner product. So in a sense, it's similar to example 1. I mean, the conditions that we had before are the same. If is absolutely continuous, derivative in L2, boundary values. The difference is here. I define a different inner product on it. The verification that this one is an inner product, the norm is complete. This is an exercise in, course like function analysis. We have done it, for example, 1, and I leave it to you to do it for this example. So exercise, verify that H is an RKHS. That's not difficult. I mean, even the fact that evaluations are bounded, it's not a big deal. We can do that. And now we want to find the reproducing kernel. The question we want to study in detail. Find KX. All the time, what is our starting point? All the time, our starting point is the fact that f of x should satisfy this for all f in this space. Bonjour. Oui. J'ai pas réservé le local, mais Catherine, est-ce que vous avez de cours ici? En effet, j'étais dans mon bureau et mon ordi a arrêté de fonctionner. C'est pourquoi je suis venu ici. C'est Catherine qui m'a envoyé. Notre dépanne, c'est de quelle heure à quelle heure? Est-ce que vous pouvez, s'il vous plaît, contacter Catherine pour voir si elle... votre dépanne, c'est pas pour le département de maths? Catherine Lévesque, qui est notre secrétaire, elle dit que, en effet, c'est elle qui m'a envoyé ici, elle sait quoi faire. Merci. Well, hope that they don't kick me out of this room, because it seems that from 4 it is reserved for a TA, but well, we will see. Oof. Our starting point all the time is this one. F of x is equal to f inner product with kx. And now, as before, even though I have good boundary values, which is okay. I mean, I don't use the boundary values, but I restrict myself. I restrict myself to the test function. So f is a test function. It's much nicer than a general element of age. And now I want this to be true. And f of x is equal to f kx, which means that now let's see what is f inner product with k. In this case, it's integral from 0 to 1 ft kx of t. This part is already good, plus f prime t kx prime t dt. Very good. I keep the first integral 0 1 ft kx t dt. No action is needed for this one. And for the other one, for this part, I do precisely as in the previous 2 or 3 examples. And it gives me minus integral 0 to 1 f of t kx double prime t dt. You see, this is the point that I use test function and distribution theory. F of 1 is equal to 0, f of z equal to 0, not because of this assumption, not because of this, because I use test functions. But I end up with the same integral I had before, and this I want to be equal to f of x. In other words, dt. In other words, if I compare with what we had before, in other words, this is the integral of f with respect to the delta function or delta measure. Our equation this time is kx minus kx double prime is equal to delta x. We have some boundary conditions too, but at the point this point, I'm just worried about the equation and how to find a solution for that. Well, how do we obtain the solution for this? We can, well, if we don't want to go to the general techniques that use in the distribution theory, we can do it this way. Just recall what we did in the previous case. I temporarily
delta x will be replaced by the ux prime.
I'm sorry, I didn't hear well.
Delta x will be replaced by the ux prime, and we will be in the OD regular.
I don't get your point. We have a differential equation of degree 2. The difference between the previous case and this case is that we have, if I call it y, we have y minus y double prime is equal to delta x. In the previous case, we had just minus y double prime. So now I want to solve this. And let's see how we did it in the previous case. In the previous case, so temporarily, when we had minus y double prime is equal to delta x, we adopt the point of view of engineers saying that delta x is equal to 0 before x and 0 after x. At point x, something bizarre happens. They are not able to explain what happens, but I mean, with our tools, we can do that. So the equation we have here is minus double prime is equal to 0 for t equal less than x, and also for t bigger than x. At the end of the day, we have something like this. And so what we did, in fact, we solved each equation independently. Here we found alpha t plus beta. Alpha, for example, it was c, beta was d. And here another form constant, gamma t plus eta for t less than x from t bigger than x. And now we try to find alpha, beta, gamma, and eta. What are our conditions? First, we want to be continuous at point t equal to x. In other words, y at point x plus should be y at point x minus. This removes one of the constants. So we ended up with 3 constants. And then we continue and obtained more, try to fulfill more conditions and obtain all the values of alpha, beta, gamma, and eta at the end of the day. That's, a very panoramic view of what we did in the previous case without mentioning such details. So why not doing the same here? We have y minus y double prime equal to delta x. We want to solve this equation. Instead of kx, I wrote y. So what we have is indeed y minus y double prime is equal to 0 for t less than x, and the same thing for t bigger than x. So what I need to do is to find the solution of this equation first. Then there are other calculations to do. How can I obtain the solution of y equal to y double prime? This is elementary. Y equal to y double prime equal to y, the general solutions. And that is why you can write the general solution in many different formats. It is true that e to the x and e to the minus x are solutions. So one can write c1 e to the x plus c2 e to the minus x. Perfectly fine. Absolutely no problem. So we can write c1, c2 for this case, and c3, c4 for this case, and go ahead and find the values of c1, c2, c3, and c4. But that's not the only way that we can write the general solution. Let's write it in different formats too. We can also write, say, d1 sine hyperbolic x plus d2 cosine hyperbolic x. That's another way to do it, because sine hyperbolic and cosine hyperbolic, they are also combinations of ex and e minus x. So vector space of dimension 2, we obtain the same vector space. That's good. We can write it this way too. And please let me change x to t, because the equation was in terms of t indeed. And also I can write e1 sine hyperbolic 1 minus t plus e2 cosine hyperbolic 1 minus t. That is also acceptable too, because first of all, sine hyperbolic 1 minus t and cosine hyperbolic 1 minus t, both of them are solutions of the equation, and they are independent. So that's one way to justify it, a vector space of dimension 2 element of the basis. Another way, expand. And you see that you obtain a combination of e to the t and e to the minus t, of course, with different coefficients. So that's another way to justify it. So any of these is acceptable. I mean, and there are other formats. So why I mentioned this? Because again, it is true that I did the calculations with C1, C2, C3, C4. I went up to the n. And then I realized that it's easier to find the coefficient if I write other formats. So I went back and rewrote my solutions like this. So my solution, I write it this way: yt equal to, for t less than or equal to x, for t bigger than or equal to x. Even I can write equal, doesn't matter. Any of these are acceptable. But I choose this one for t less than or equal to x. So alpha sine hyperbolic t plus beta cosine hyperbolic t. And for bigger than 1, I use the third one. I use gamma sine hyperbolic 1 minus t plus beta cosine hyperbolic 1 minus t. And you immediately see the way I kind of, it's true that you may say I cheat. I want my kx of t to be one of these yt. True. So what are the conditions that they are there to be satisfied? Well, boundary conditions. I need to be in this space. I need y of 0 to be 0. And what is y at point 0? At point 0, we are there. And when I put t equal to 0, is alpha times sine hyperbolic 0 plus beta cosine hyperbolic 0, which is just beta. So my beta is equal to 0. And why at point 1 also I want to be 0. Y at point 1 is gamma sine hyperbolic at point 0 plus alpha beta gamma, this is eta, plus eta cosine hyperbolic 0, which is eta. So eta is also equal to 0. So immediately 2 of the constant need to be 0, and my y simplifies to be alpha sine hyperbolic at point t and gamma sine hyperbolic at point 1 minus t. I succeeded here to immediately obtain beta equal to 0 and gamma equal to 0, because as I said, in a sense, I cheat. At the very beginning, before, when I wanted to prepare my talk, here I wrote C1 e to the t plus C2 e to the minus t, and put here my condition was C1 plus C2 equal to 0. So it's just one condition, C2 equal to minus C1. I replaced and simplified, and I obtained this one. So that is why I went back to avoid those calculation. I wrote my general solution as this, which gives me beta immediately equal to 0. And the same for the second one. It was more involved in the second one because I had to evaluate the function at point 1. So if I use this one with C3 and C4 at point 1, even it's more involved, but still, when I did the calculation, I saw that, oh, at the end of the day, I obtained this one. So that is why those formats were adopted to obtain a simpler solution. There is one more thing to be satisfied, and gamma at the point x plus should be equal to gamma at the point x minus. In other words, the function has to be continuous. And this means that alpha sine hyperbolic x has to be equal to gamma sine hyperbolic 1 minus x. So again, one coefficient or one constant less, because it's a relation between alpha and gamma. I can remove alpha or remove gamma and put it back in the formula, or call everything lambda. And now my y of t is of this format. Alpha is lambda divided by sine x, sine hyperbolic x, times sine hyperbolic t. And gamma is lambda divided by sine hyperbolic 1 minus x. At this point, I can say with certainty for any values of lambda, y is in my space H. It's a function which is absolutely continuous, and at the point 0 is equal to 0, at point 1 is equal to 1. So this is good. And now I have one more restriction, and the restriction is that it has to satisfy either the differential equation that we had above, this one, in order to be, this is equivalent to be, because the boundary conditions are the same, y to be k of x. Either this equation has to be satisfied, or we, as in the previous examples, we verify what is the inner product of an arbitrary f with this, and when do we obtain the f of x precisely. Both methods are good. For example, if we want to verify the differential equation, then starting from this definition, we see that y prime is equal to lambda. Prime is with respect to t. Here is sine hyperbolic x, cosine hyperbolic t for t less than x, and for t bigger than x is minus lambda sine hyperbolic 1 minus x cosine hyperbolic 1 minus t. I didn't write less than or equal x or bigger than or equal to x. Indeed, at the point x, the derivative does not exist in the classical setting. If we look at this from the distribution point of view, the function that we have is like this. At the point x, before x, it's a nice function of cosine hyperbolic, so it's something like this. I don't draw the precise graph. I want to see what's happening. And after x, it's another graph. There is a jump here. There is a jump here. So here we want the function to be the derivative we want to be in L2, but it's way more than that. The function we have here is C infinity. This one is also C infinity because it's cosine hyperbolic. But at the point x, there is a jump. And now we want to calculate what is the second derivative. And to obtain the second derivative, let's see what is this delta, the jump. Y at the point x plus minus y at the point x minus. You have the formula for t bigger than x. This gives you, this part gives you y at the point x plus, and the other one y at the point x minus. So you obtain minus lambda here sine hyperbolic 1 minus x cosine hyperbolic 1 minus x. This is x plus minus, for x minus is this one, lambda over sine hyperbolic x cosine hyperbolic x. It looks a bit complicated, but you can simplify, factorize lambda sine hyperbolic x sine hyperbolic 1 minus x. What you have in numerator now is sine hyperbolic x cos hyperbolic 1 minus x plus sine hyperbolic 1 minus x cosine hyperbolic x. And this is the formula for sine hyperbolics alpha plus beta, x plus 1 minus x. So it simplifies to, I'm sorry, it simplifies to minus lambda sine hyperbolic 1 sine hyperbolic 1 minus x sine hyperbolic x. And therefore, you remember recall, when you have a jump at point x, the derivative is delta x. So if you multiply both sides by a constant, you have delta ux prime is, delta ux prime is also delta x. It's a jump by delta, and we have this jump here. So if I want to use this formula and find y double prime, so what is y double prime with respect to t? And here is the place you need to be careful. For t less than x, the derivative of this is lambda over sine hyperbolic x sine hyperbolic t less than x, t bigger than x is the derivative of this part minus, with minus here, it becomes plus. So it's lambda sine hyperbolic 1 minus x sine hyperbolic 1 minus t. That's not the end. That's the derivative of right side, left side, but there is a jump. So it's, you have plus delta x. This is the part that I wanted to add here. I added here without going into detail of distribution theory. You need to be careful about this. And then, I mean, just observing this, you see that this is precisely equal to y that we had before. So y double prime is equal to y plus delta x, or what was our equation? Our equation, I think it was y minus y double prime. Yes, here it is. Here it is. Y minus y double prime is equal to delta x. So y minus y double prime is now minus delta x. So what we need, therefore, minus delta should be equal to 1. That's the condition I wanted to obtain. And what is delta? It's here. Here is the formula for delta. It gives me lambda. So lambda is equal to, I write the formula, sine hyperbolic 1 minus x sine hyperbolic x over sine hyperbolic 1. Plug it back in the formula. So kx of t, which is our y of t, now it becomes rather unexpected formula. Sine of 1 minus x over sine hyperbolic 1 times sine hyperbolic t for t less than or equal x. And note that there was sine hyperbolic x in the denominator, which simplifies. The same for the other one. Here is sine hyperbolic x. The one with 1 minus x simplifies. And here we have sine hyperbolic 1 minus t for t bigger than or equal to x. This is our kernel. I mean, when we started the example, I believe nobody expected to arrive at such a formula at the end. And more interestingly, what is Ax, its norm, as a bounded operator from H to R. It's root of Kx evaluated at the point X. Therefore, norm of Ex is equal to either this one or the other one. I mean, at the point X, they coincide. So it's sine hyperbolic 1 minus X sine hyperbolic X divided by sine hyperbolic 1 root square. Oh, I mean, it's absolutely impossible to find this from scratch. And that shows the power of, I mean, RKH. Without RKHS, we were not able to find the precise value of norma Vx. Is that good? Okay, well, I'm glad that the lady didn't come back and we still stay in the room. Apparently they found another solution for her. So let's have another break. I mean, say another, it's 16:16. We come back at say 25, and then we have another session to continue. So a little break of 9 minutes.